Hello everyone! Today we are moving to section 1.9 and continue working with matrix transformations, considering compositions of matrix transformations. So imagine that we do have two matrix transformations. Transformation A, which takes or reflects space with n dimensions onto space with k dimensions. And the second transformation, transformation B, which reflects space with k dimension into space with m dimensions. Then guys, we can define the composition of these two transformations, B over transformation A. And that transformation is going to be from Rn into Rm. Let me show you how it's going to look graphically and then how to calculate or how it's going to look as a matrix. So I'm going to have my first Rn, second Rk, and the third Rm. So let's imagine that my first transformation takes elements from this set and kind of transforms it into elements of another space Rk. And then other transformation takes elements from this space and transforms them into elements of my final space with m dimensions. So we can kind of substitute as one transformation. Basically what we have is TB over TA is going to be what? Transformation B applied over transformation A, which is in its turn applied over vector X. And that's going to produce a final vector W, for example. Okay. What can we say about this transformation composition if we have matrix transformations? Well, we do know that TA is actually what? That's just A multiplied by X. And dimensions of this matrix are going to be K by N, right? And then if I apply one more transformation, which is also matrix transformation, I'm going to multiply it by matrix B, right? And that matrix is going to have dimension M by K. And finally, guys, what I can say, well, because we have this associative law for matrices, we can write down that basically this is B, matrix B multiplied by matrix A and multiplied by vector X. And this can be called a matrix of composition. So matrix of composition is going to be the product of the matrices. I'm going to call it TBA, matrix of composition, and that's going to be just a product of matrix B by matrix A, or a product of matrix of transformation B by matrix of transformation A. Well, let's consider example. It's not complicated, just like let's consider example. I'm going to just use a book example, example number 1. First transformation is going to be, it's supposed to be 2 dots. First transformation is going to do R3 into R2. And transformation is going to look like this. I'm going to just give you the formula. X, Y, Z, three-dimensional vector. It's going to convert into X plus 2Y, X plus 2Z minus Y, two-dimensional vector. My second transformation, T2, is going to take two-dimensional vector and convert it back into three-dimensional vector. And it's going to have a different formula. The formula is going to be taking two coordinates x, y, and converting them into three coordinates. 3x plus y, x minus 2y. Well, let's just maybe find that transformation or like composition of T2 by T1. What is going to be the matrix of composition? Well, guys, first we are going to start with writing down matrices of transformation 1 and transformation 2. So I'm going to label them with letter A because transformations here are not different by letters but different by indexes, index 1 and 2. So my first transformation, A1, is going to be the coefficients of my functions. Well, I'm sorry. So if you write it down like W1 equals this and W2 equals this, what are going to be the coefficients? The coefficients are going to be 1, 2, 1, 2, and 0, and 1, 2 minus, oh no, 1 minus 1, 2. Sorry, I kind of messed a little bit like how it was written. And like if you want to like see how the final vector is going to look, the final vector is going to look like this. W1, W2 is going to be this matrix A1, 1, 2, 0, 1 minus 1, 2, multiplied by x, y, z. So you take x, y, z, multiply by this 2, and you are going to get the result, okay? So that's my first matrix. My second matrix. Well, I'm not just going to maybe explain more. Here for second matrix, we have just two components, and we are going to have three resulting equations. So I'm going to have 3, 1, the coefficients, and then 1, 0, there is no y here, and 1 minus 2. That's going to be my second matrix. And if you want to write it down like the system of equations, I'm going to have W1, W2, W3, my image. And that's going to be the matrix 3, 1, 1, 0, 1 minus 2, multiplied by x and y, the column vector of two dimensions. R2 into R3, right? This one doesn't look like 2, but okay. So what we can do, just according to our kind of representation of the composition, to find composition, you just need to find the product of these two matrices. Let's do it. Not supposed to be too difficult. Let's see how it's going to work. So if we apply second composition to the first, we are going to use matrices in the same order. So I'm going to write down maybe A3, and that's going to be composition. It's going to be A2 multiplied by A1. And I'm just literally going to write down these two matrices, A2 and the other matrix. Well, I'm going to do multiplication, but please check me because I do mistakes sometimes. So I multiply the first row by the first column, and I have 3, 1 and 1, 1, so it's going to be 4, right? Second row by the first column, just 1, and the third one is 1 minus 2 minus 1. Okay. Now, first row by the second column, 6 and minus 1, looks like it's 5. 1, 0 by 2, 2. 1 minus 2, 2, 2, plus 2, 4. Well, again, 3, 1 by the last column, 3 by 0 is 0, 2. 1, 0 by 0, 2 is 0. And 1 minus 2 by 0, 2, minus 4, I think. Well, again, maybe I did a mistake somewhere, but we got a 3 by 3 matrix. Why? Let's look at our composition. So we start with this one and we finish with this one. So we go from 3 to 3. Supposed to have 3 by 3 matrix. So that's our composition matrix. Okay. Oh, well, that's very good. I think we can consider a composition of real reflections and projections. maybe in class as examples, because basically if you do know matrices of each element, you just multiply them and that's going to give you the result. But you also can do this composition on like basis vectors and get the result. Maybe I should consider one example. Let's do one example. So example number 2. Well, I don't know. Let's consider, for example, reflection and projection. So I'm going to write down T1, reflection about x-axis, and T2, projection on y-axis. Okay, so let's see what is going to be the composition of these two. Well, again, guys, you can find reflection on x-axis, you can find projection on y-axis, two matrices, just multiply them. I'm going to show you how you can do it differently. You can actually apply transformation, which is like this, the 2 steps, and then kind of see what happens to your standard basis vector. I'm going to do that actually. I'm not going to do it the standard way of multiplication of matrices. So what I'm going to do, I'm going to apply T1 to E1. And of course, I'm going to draw the picture and see how the picture is going to be affected. So that's my x-axis, that's my y-axis, and that's my first vector, E1, right? So start about reflection about x-axis. Well, reflection about x-axis makes nothing to this one, right? Just like a reflection about the same axis. Projection onto y-axis is going to turn it into 0, 0 point. So actually, that's going to be 0, 0. Well, maybe that's not a good idea to do these two transformations, but I want to just show how it works. Now, guys, I'm going to do T2, T1 onto E2. Okay, E2 is going to be a vector along y-axis, E2. So what is going to do reflection about x-axis? Well, reflection about x-axis is going to do this one. So it's T1, E1, right? That's a reflection about x-axis. Now, what is going to be projection onto y-axis? Well, basically the projection onto y-axis is going to be the vector itself, right? So what are the coordinates here? Well, x coordinate is 0 and y coordinate is -1. So now my composition matrix T2, T1 is going to be just the first vector 0, 0 and the second vector 0, -1. And guys, I'm leaving it for you at home to verify that you are going to get the same result if you just calculate matrix of this, and then multiply them, T2 by T1. Are you going to have same? The question. Okay. Well, maybe I'm wrong. I did something, miscalculated it, but most likely everything is going to work. Okay. Now, guys, let's talk a little bit about like beyond composition, more definitions. Okay, move this up and talk about definitions. Definition: matrix transformation TA from Rn to Rm is 1-to-1 if it maps different vectors from Rn into different vectors in Rm. I'm going to draw the picture. Well, one-to-one idea is the same as with functions. So you take like different vectors, x1, and this is t of x1, and x2, and this is t of x2. So it takes two different vectors and kind of transforms them into two different vectors. Not every linear transformation is supposed to do this. But this is called one-to-one. So for one-to-one, if x1 is not equal to x2, then transformation of x1 is not going to be equal to transformation of x2. If you have two different vectors, the results are going to be also different. Okay? Okay, well, which transformations are one-to-one, which are not? I'm not going to actually maybe consider them a lot, but you probably already see like what we had. We had rotation, reflections, and projections. So rotation is usually going to take a vector and transform it into something different, right? And two different vectors are going to stay two different vectors. Reflection also, two different vectors are going to stay two different vectors. So one-to-one, reflection and rotation. On the other hand, not one-to-one, projection. For projection, maybe I'm going to show you, like when you do projection, you can take this vector or you can take this vector and they are going to be projected into the same vector. So two different vectors project into this one, which is like violation of the one-to-one statement. Okay? Okay, why do we need one-to-one? Well, guys, now imagine that we have a matrix operator definition. If matrix transformation from Rn to Rm with invertible A, then we are going to call transformation Ta invertible. And we are going to label it next way. Ta inverse. And actually that's going to be transformation with inverse matrix. Well, maybe I should explain a little bit like why inverse transformation is going to have like inverse matrix as a like matrix of transformation. Sorry guys, I pressed something and my whiteboard disappeared. Okay. So, what is going to happen if you apply two transformation with inverse matrix, well, considering that matrix has inverse, and transformation with kind of like direct matrix or like original matrix? What is going to happen if you apply this two transformations as a composition? Well, we know that the matrix of composition is just a product of these two matrices. So we are going to have, A inverse multiplied by A. And if matrix A is invertible, then A, I put inverse in the wrong place, sorry. Inverse. If you multiply direct matrix by inverse, we are going to get what? Identity matrix. And identity matrix is going to be what? Identity transformation. So basically, if you apply this transformation to some vector x, that's going to be same identity transformation by vector x or vector x itself, which is actually kind of description of inverse, right? Because when you take direct transformation and inverse transformation applied to x, you're supposed to get x. This is cancellation equation. And that's how we kind of define inverse. So this is Ta And we need to go back to original x, and that's going to be T inverse A. So, well, basically, guys, with matrix transformations, everything is kind of simple. If matrix is invertible, then transformation has inverse. If matrix is not invertible, transformation does not have inverse. Well, we remember probably when matrices are invertible, right? Some kind of clues. For example, determinant is not equal to 0. So matrix is going to be inverse. Or like matrix has inverse when all rows are linearly independent. Another thing, another way to kind of find it. Okay, that's all about like compositions. I'm not asking you to find inverses, but actually, interestingly, that you can find inverse to the matrix by using the idea of transformation. I think we are going to touch it in class. I'm going to consider a couple of examples in class, how we can find inverse matrix by actually using the idea of inverse transformation. Okay, that's it for today.